Hey folks, this is Todd Coburn of Cal Poly Pomona with lecture 16 of Aero 4080. Today we're going to be covering two topics. One is NASTRAN's replication feature and the other is buckling. Stay tuned. So first we're going to look quickly at replication and how it works. It's actually quite simple. NASTRAN's replication feature works like this. So first of all, you're going to need, normally in your deck, you're going to have a card in the bulk data section, and that's where this feature works. You're going to have a card like a grid card, or a C-bar card, or a C-rod card, or whatever. And if you want, what you can do is once you've specified at least one card in its completion, on the next card, you can work off of the prior card by placing similar information, only the information you want to change. For example, for each field, so we have 10 fields, right? For each field, we're going to have, if we want it to be identical to the prior card, then the card that follows will have an equal sign in that field. For example, if you have a grid card and you want to use a grid card again, then you can have equal in the first field. The next field is the ID number. It needs to be unique, so often what we'll do is we'll increment that by 1. I'll show you how to do that in a minute. So what we can do is put an equal sign in each and every field that we want to be the same as the prior card. If you're using the fixed format, then basically you're going to have an equal sign, and then 8 columns later you have another equal sign, and so on. If you're using freeform, you're going to have an equal sign, comma, equal sign, comma, and then so on. Now, if you want everything in that card, that following card, to be the same as the prior card, everything in the rest of that line, then you'll place two equals together. So, if you place an equal sign in any given field, that makes that field the same as the prior card. If you place two equal signs together, it automatically says, from here onward, everything is identical to the prior card. Now, if we want, say, to change one of the fields, we can change it by a specified number. So let's say we have a grid card and we want to change from grid card 1 to grid card 2. Then instead of putting an equal sign in that particular field, we'll have a star 1, which will increment that number by 1. If you wanted to have all your grid numbers to be like 100, 200, 300, then your first grid card ID would be 100. The second would have an equal sign, meaning it solves another grid card. And the next field would be a star 100, which will go from 100 to 200 and so on. If you want it to be 1, 2, 3, your first card would say 1 in the ID. The second card will have an equal sign and then a star 1, which will make it 2 now. It'll add 1 to the prior number. And then after that, the next field, you have equal, equal, and that makes the rest of the card exactly the same. Okay? Now, if you want to then repeat the entire card a certain number of times, so let's say you have a grid card, and then you have a incremental where you're saying, hey, it's the same grid, and you're going to increment the ID by 1, and then you want to do that same procedure another 5 times, you'd say equal 5, and that will give you 5 more. So if we made a card with grid ID 1, a grid card with grid ID 1, the next card you have equals, comma, star 1, comma, equal, equal, will give you the exact same card, except the ID is now 2. If you then have on the next field, you just have equals 5, what that means is it will read that card and it will say, oh, I want to do that same increment 5 more times. So what we would see is a card with a grid point with ID 1 created with the placement that you said. The second one would be grid ID 2, and then you'd have grid ID 3, 4, 5, 6, 7. You'd have 7 total grid points. Of course, if you did this a procedure, this would put them all at the same place. So if you want to move them, like let's say you want them in a row, you want to be, say you have one at 0, 0, 0, and the next one at 10, next one at 20, next one at 30, then in that second field, you'd say equal, comma, star 1, comma, comma, for the coordinate system, and then in whichever field you want to increment, like in the X field, you'd now say star 10 point, makes it real, comma, equal, equal. What that will do is your first card is at 0, 0. The second card increments the ID by 1 and the X position by 10 and so on throughout the rest of the cards. That's how it works. We'll see some of that in a minute. I'm going to go ahead, and after this we're going to switch to discussing buckling. But as we discuss a buckling, how to run buckling, we will then look back at, because I'm going to use replication for developing that model, and you'll see how that works. Okay? Stay with me. Also, one more comment. NASTRAN also has a feature called MSG Mesh. If you get Schaefer's text or something like that, that describes that. I have used that a little bit. This replication feature is a very powerful feature. By the time you get to MSG Mesh, it's better, in my opinion, to use the pre and post buckling, the pre and post processing capabilities available in PATRAN or FEMAP. Okay. Now you're going to find if you become a really prolific user in FEMAP or PATRAN, and we're heading toward that part of the class, then you will probably find you're going to like creating your models there within FEMAP or PATRAN. It'll be a little more efficient for anything more than a simple model. If you have actually mastered everything I've taught you to date, you will find that for simple models, it's easier just to create the bulk data file by hand. And replication adds more speed to how you can create a model really fast. One caveat: replication doesn't appear to work in Autodesk NASTRAN. It looks like they do not recognize that feature. It does work with other versions of NASTRAN, maybe not all of them. So if you are using the MSG, the MSC, the McNeil-Schwindler version of NASTRAN, then replication should work for you. If you use NX NASTRAN, then this should work for you. If you use Autodesk, I don't believe it will work. Okay? So now we're going to look at buckling. But before we do, let's take a quick look at this deck here, this NASTRAN deck. Let's ignore that it's got a couple different cards that make it unique for buckling. And let's focus first on just the replication that's being implemented. So you'll notice in this model, let's just annotate this as we go. We see if we take a look at our grid card, the grid card here, we see that we have our first node here. It's node number 1, and it's located at 0, 0, 0. Okay? And then we see the replication card. So we see we have another grid card. It's going to increment the ID by 1, so that's going to be grid 2. It's going to have the same blank standard coordinate system, which is the global coordinate system, and then it's going to increment the location, the X location of the first node by 20. So that means it's going to place node 2 here at a distance of 20 units to the right, or in the positive X direction. In this case, this is our positive X. It's going to then do that 3 more times. So it's going to do the exact same thing in another 20. It's going to put node 3, which is incremented by 1, in another 20. It's going to do node 4, and in another 20, it's going to do node 5. You see, this node 1 was generated by this card, node 2 was generated by this card, and nodes 3, 4, and 5 were generated by that card. We then identify a C bar. It's got ID 1, and it's going from grid point. It's using property card 1, and it's going from grid 1 to grid 2. So that means this is C bar 1, and it has property card 1, and it has, and then it's going to be located, so that means we're going to be from 1 to 2 is our X, and then 0, 1, 0. So if that's X, then 0, 1, 0 is this vector defining Y. That means Z is coming out of the page toward us for that first bar. So that defines this as the Y for that bar. Then ignore this. This is part of a comment that's dropped from the other line. We see we're going to have equal sign. This equal sign means we have another C bar. It's going to be ID number 2, and it's going to be going from, using the same property card, it's going to be going from whatever the first ID is of the first card plus 1 to the ID of the second plus 1, which means it's going from 2 to 3. So bar 2 goes from 2 to 3. And then we're going to do it twice more. So we're going to get bar 3 going from 3 to 4, and bar 4 going from 4 to 5. That is the beauty of replication. We then have property cards and material cards and constraints. We see at node 1 we've got 1, 2, 3, and 4. And at node 5 we've got 2 and 3, which means it's constrained out of plane this way, and it's constrained out of plane toward us, but it's allowed to move in the x direction. You see that? We then have a force 1,000, the minus x, placed at node 5. 1,000 units of force, which in this case is pounds. So that is our model, and it was generated with replication. Once again, if you have Autodesk NASTRAN, it will not recognize replication. If you have MSC NASTRAN at will, and I believe NX NASTRAN does as well. Actually, both of those do, or should. NX does, and I believe MSC should also, since MSC, I believe, is the one that developed that initially. Okay? So, with all that said, now that we see how replication was implemented, we can focus on the buckling solution. The buckling solution, remember back in arrow 3261, we learned about buckling of columns. And we learned that if we have a column, let's say it's pinned column, and we put an axial load, we saw two ways. One way, we pretended it was a couple rigid elements with a little spring here, and then we went and we solved the differential equation, the bending differential equation of this beam, and we found that both of those provided a solution that gave us P critical. How to calculate P critical. P critical is the last force that can be withstood before we get a drastic change in the deflections. So we learned about that in 3261. Then in 3271 we looked at panels loaded in compression, or loaded in shear, or loaded in bending, and we looked at those failure modes separately and together. We looked at curve panels, and we looked at cylinders for buckling. All of those buckling solutions, we have to be careful not to buckle our structure lest it doesn't retain the loads. And what solution 105 does, if we want to find out this kind of buckling, the easiest way to do that is use solution 105. Instead of 101 for static, we're using 105 for an eigenvalue kind of analysis. And what that will do is the eigenvalues will determine what factor of our loads were applied. So let's go back to our initial. If we have a rod located axially, as this one in this particular model is, except that one was a horizontal rod, with an axial load, basically a pinned column, we saw what the K was. We saw the same thing for a panel. Now remember, if we have this case where we have a column loaded in buckling, then this solution 105 will come up with a set of eigenvalues, and the minimum eigenvalue will be a factor of this load that was applied and what the buckling solution is. So let's say our eigenvalue is 1. That means whatever force we applied, in this case 1,000, if we got an eigenvalue of 1 and we applied 1,000 pounds, that means that 1,000 pounds, 1 times 1,000, is exactly how much, what the critical load is. That's the P crit for this structure. Let's say we apply this 1,000 pounds to a different model and we get an eigenvalue of 2. That means that the critical buckling load is 2 times whatever the force was that we applied. If this eigenvalue is 3, then the critical buckling load is 3 times whatever we applied. If the eigenvalue is, say, 0.5, that means 1/2 of whatever we applied is the critical buckling load. See how that works? Now we're going to find out in a minute. Now often what we're going to do is we're going to get a bunch of eigenvalues. We're going to get an eigenvalue for every part in the model, every point, and then we're also going to get an eigenvalue for different modes. Remember when we were looking at the compressive buckling of panels. So let's say we have a panel buckling in compression like this. We saw the factor, the coefficient of buckling that we applied for our critical buckling load. Remember it did this? And we saw this was the first mode, and if it doesn't fail there, this is the second mode. So actually, if the first mode doesn't fail it, the second mode might. And if the second one doesn't, the third mode might. So what's going to happen is if we pull back various eigenvalues, the first eigenvalue will be the lowest eigenvalue. The second eigenvalue will be the next one if it doesn't fail in the first one. The reason this is valuable is because a lot of times with these structural models, we will get, or sometimes we'll get an eigenvalue from a point that can't possibly buckle in the direction that the model thinks it's going to do. Therefore, when we identify that yes, this is a mode that cannot be associated with buckling, we can eliminate that and ignore that one, or actually explain why that one's not valid, and go to the next eigenvalue, which then becomes our critical eigenvalue. Okay? So that would be the reason we might want to report multiple eigenvalues. Now when I say multiple, once again we're talking there's a difference. We're going to get an eigenvalue at each point in our model, but what we're talking about is we're going to get the first eigenvalue and then the second set of eigenvalues and the third set of eigenvalues. That's what we're talking about. The first set of eigenvalues is critical unless they can't occur, and then the second becomes critical. So in order to implement buckling, a structural buckling kind of problem, the easiest way to do this is to use solution 105. We're going to do that by using the solution card. We're going to call that 105 instead of 101. We're then going to, one sidebar, remember we've been using this title to identify our models. You'll notice on the first NASTRAN deck that I posted, I used the label card instead of subtitle, and you may have noticed that the label card doesn't put anything in your output. But if you use the subtitle card, it will put whatever's here on the top of every page of output, except for the pages associated with the subcase. If the subcase has a subtitle, then what happens on any output for that subcase, that will have this title rather than that title. But this subtitle will be on all the rest of them. Does that make sense? Okay. One other caveat here. We'll see this S vector. Okay. So the first card we need is this solution card. The second card we need is this method card. Okay. The method calls out what method is going to be used to extract eigenvalues. And what it calls out is just an ID. ID 13, if we look down here, ID 13 is associated with this eigenvalue card called an Eigerl card, okay? So what this basically says, the method card says this is the ID of what method I'm going to use to get the eigenvalues. We'll look at what card this is now, but there are different cards that we can use to extract eigenvalues, and we'll look at that in just a minute. Are you still with me? Okay. So we need the solution card, we need that's here, we need the method card, we need this S vector card. So this isn't required, but what this does is we'll bring back all eigenvalues. At each and every node it will bring back the eigenvalues. That is useful in understanding how the model runs. So it's called S vector equals all. You'll notice here I have it left justified, which is fine, but actually in order to be consistent, what it should have been is aligned with all this stuff. All this should have been indented because that's all part of this subcase 1. It doesn't change anything with NASTRAN, but it's easier to understand what's going on. Then we have the bulk data deck, which we already talked about a little bit. You'll notice we still have SBC cards and load cards just like before because we need to call out our SBCs and we need to call out our forces. Okay, the next card that's new is the Eigerl card. That's the card that we're going to use for eigenvalues. We can actually use the Eiger card or the Eigerl card. We'll look at the Eigerl card in a minute. That's just using the Langskos method for calculating eigenvalues Okay. Basically, what that card here is doing is it's saying, well, we're going to use this method, the method associated with iGirl, the iGirl card. 13 is just the ID that we specified before. And now I've skipped over some unnecessary inputs that you can use once you get a little sharper in this stuff. And basically what this 5 is, it says I'm going to pull back 5 sets of eigenvalues. I'm going to pull the first set of eigenvalues, the second set of eigenvalues, the third, fourth, and fifth. Normally all we're concerned about is the first. That's all we need. That's the only one that matters. It's the lowest one. The reason we're pulling back 5 is because there are reasons why we might sometimes eliminate one of those modes and say, hey, this doesn't actually apply to our model. Our model can't buckle in that way. For example, if you didn't constrain the model out of plane and it had some marginal stiffness, it might have then dialed in and out of plane in this direction failure mode. And if you're like, oh no, this is between two concrete walls, it can't move that direction, you can ignore that eigenvalue and go to the next one. Make sense? Okay. There is one other card that's not associated with buckling, but that we will use as our models get bigger and also is useful for this model. And that's the parameter auto SPC card shown right here. Auto SPC, what that does is it automatically constrains any degrees of freedom that look too soft. This is useful. Let's say we have a two-dimensional model and we calculate all of our nodes and properties in this plane and we don't restrain it out of plane. Now some of you are starting to get sharp and you're learning to extract or constrain the third degree of freedom. We put a 3 in for each and every node, which keeps it from moving that way. If we hadn't done that, the model would be singular and would not probably run. What the auto SPC card does is says, hey, look, looks like I got a spongy spot that probably wasn't intended, so it just purges those from the solution sequence. Okay, so this card is a little dangerous because what it means is it may be constraining things that NASTRAN sees as spongy that actually might be a real spongy spot on the structure. However, even though it's a little bit risky to use this card, it's very common to use this card, especially as your models get larger and larger and larger with complex connections, and it's easy to miss something, and a lot of times folks will rely on this card maybe a little bit too readily. Okay, so that is the buckling, how buckling works, and that's the set of cards for buckling. So let's go ahead and look at some of the other cards in more detail that we have used in this particular slide. So we saw the method card, and the method is just calling out what basically we're going to call out method structure, and I believe that in parentheses structure part can be eliminated for most models or most NASTRAN versions. You're just going to put the ID of whatever this NASTRAN deck you want, whatever eigenvalue card you're going to use. In this case, we're using the iGirl card. Okay? Then we've got the S vector. Once again, S vector just brings back all of our eigenvalues, okay? And we want to bring those back to print, and you can just say S vector equals all and ignore what's in the brackets there. Auto SPC, we've already looked at how that works. You know all about that. Oh, excuse me, this is not auto SPC. This is the parameter auto SPC. And what this basically does is constrain any super soft degrees of freedom. Once again, it's dangerous, but it can be useful. The next card is our iGirl card. If you look in your NASTRAN book, you've got the iGirl card, you've got the iGirl card, there might be a couple others. iGirl just uses Lanskos method, allows you to do a number of things. Basically, the minimum that we're going to need for most of our stuff is just what the name of the card is, what the ID is, and how many eigenvalues you want to bring back. And usually about 5 is a good number. Okay? Okay, this slide is just reminding us. So we're gonna, once we start using this for our buckling analysis, we then are gonna want to do hand analysis to verify that. And this is just reminding you how to calculate the critical buckling load. Go back to your 3261 manual. It shows how to calculate the buckling allowable for columns. If you have a model consisting of a bunch of plates, like let's say you model a plate loaded in compression, you would then go and use what we learned in 3271 for predicting the critical buckling load for that plate and compare that to your NASTRAN solution. That is all I have. You've learned two new things. You've learned how to do buckling analysis, so you know when your model is going to become unstable, at what force or moment or loading. And even though we focused on a single force, which we can actually analyze by hand, we're going to find out that even if we have complex loading with shear and bending and all this other stuff on a structure, that buckling analysis can pick up on the critical buckling load if our model is correctly made and the card is used and the buckling run is run correctly. Okay. The other thing we learned about is replication, which will not help you Autodesk users, but will help anybody using NX or MSC NASTRAN. It's a very powerful tool that is super fun and puts a lot of your fingertips. If you're a really good MATLAB programmer, you could probably write your own MATLAB program that will do the same thing of generating. So this may fire your imagination for how to put in just a little bit of information and quickly make a beam model or a truss model or something like that using replication. Enjoy.